Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer them at the end and to follow up with any unanswered questions by email. As I think you know, these tech talks have been designed to provide straightforward insights into radio frequency components. We talk about various technologies and certainly about the extra design and engineering value that is added by a custom manufacturer such as Quantic Corry. To begin today's session, I am pleased to once again introduce Quantic Corry's Vice President of Engineering, Jim Price. Jim is an electrical engineer, a patent holder, and has written numerous white papers on filter design. He has been with Quantic Corry since 2004, and over the past 20 years, his passion for helping customers and solving problems has only grown in intensity. So welcome, Jim, and can you share an overview of today's topic and your objectives?
Well, thank you, Paul. Sure. So we're here to talk about diplexers, particularly high-power diplexers, and there's a lot of room for interpretation there. So I'm talking about diplexers that can handle 100 watts or so at least, maybe even up into the kilowatt range. That's what I mean by high power. And exactly what is a diplexer? It's what you're looking at in the block diagram there on the lower left corner. It's two different filters that are coupled together at a common port on one end and are free hanging on the other end. It's a 3-port device, and these devices are very handy in communication systems. The common port oftentimes is tied to an antenna, and either the high band port or the low band port is tied to a transmitter, an RF transmitter, and then the unused port is tied to a receiver, an RF receiver. The nice thing about diplexers is that unlike splitters, you don't lose half the power. If you have a low loss filter, at least you don't lose half the power from the common port to the high band port and the low band port. Instead of just splitting the RF signal directly into 50% power at two different locations, it actually routes one particular set of frequencies in a fairly lossless way to each port. So if you have a high range of frequencies that the high bandpass filter passes, and they're coming in the common port from the antenna, or vice versa, coming from a transmitter to the antenna, they'll have very, very little loss, only whatever the loss of the filter is. You won't lose 3 dB plus the loss of the filter. All you'll lose is the loss of the filter. And these filters can be very low loss if they're designed properly. And in fact, you want them to be low loss if it's a high power application, so that they don't heat up abnormally or to an excessive degree.
Okay. And to get started, what can you share with us about filter architecture?
So a popular kind of filter architecture for these is resonator structures. So I have a picture of that shown here. What you're looking at, it might be a little strange to look at, but what you're looking at is a metal housing. And inside that housing are rods that are shorted to the housing, which is ground on one end, and are free floating inside the housing on the other end. And each one of those rods looks like a shorted inductor to ground. And inside the housing, due to the capacitance from the rod to the metal walls of the grounded housing, they resonate. It looks like these look like 4 separate, in this case, 1, 2, 3, 4, 5 separate resonant structures, almost like tuning forks. They want to pass frequencies of a very, very particular frequency through that filter, and that's why they're called resonant structures. They respond to a resonant frequency or a very particular frequency at their inputs.
Okay. And what about the resonant circuitry? What would you tell us about that?
So yeah, so what these look like to the circuit designers out there are inductors in parallel with capacitors, as you see in this photo. So many of you might be familiar with the resonant structure of an inductor in parallel with the capacitor. Well, that's what these rods are. The rods look like shorted inductors, and then the capacitance from the rod to the metal walls of the housing uh, have it kind of look the equivalent of an inductor in parallel with a capacitor, and you get the frequency response shown on the right there, where you get a peak resonant sort of a structure there. Now the sharper the peak, the narrower that plot, the more spiky that plot, the lower loss and the higher quality factor of the resonator. So if the resonator has very, very low loss, that will be a very, very narrow bandpass structure. It will really only want to tend to resonate at one particular frequency.
Okay, I see. So are we to understand then that the circuitry will vary depending on the filter type? And if so, maybe could you share an example?
Yeah, sure. So the previous page was a quarter wavelength long resonant rod. This page shows a half wavelength resonant rod. The difference is the one on the previous page looks like an inductor in parallel with a cap, and on this, the half wavelength rod, one that's about twice as long, will look like a inductor in series with the capacitor, and then you get the notch or band reject response you see on the right, and the sharper the response, the better the quality factor of the circuit, or the lower the loss of the circuit.
Okay, well, how about for bandpass filters then?
So since this is a diplexer discussion, uh, diplexers are typically a high band bandpass filter and a low band bandpass filter tied together on one side, as I had showed earlier. And so for that, you want to use the quarter wavelength uh, rod structures to create resonators. And there's a particular type of filter design methodology called coupled resonator design that is well known. There's a particularly good book that I have referenced here that discusses how to design and create these kinds of filters. This book is basically instructions and a lot of tables of normalized filter parameters that show you how to design these filters. The basic concept is that you have these parallel resonant resonators, and you couple energy between the resonators at very precise levels to get the filter response that you want. And I can kind of show an example of that next.
Okay, why don't we go there?
Yes, so this is a 4-pole bandpass filter. It's got 1, 2, 3, 4, 1, 2, 3, 4. Actually, it's 5-pole. It's sorry about that. It's a 5-pole structure, and it's got 5 resonators, and each one is shorted to ground on one side. It's free floating on the other side, and they resonate at a very particular frequency. And energy is coupled from rod to rod to rod in very precise amounts by the spacing of the rods. The closer together the rods are, the more energy is coupled from rod to rod, and the further apart they are, the less energy. So if you want a wideband response, these rods are very close together. And if you want a narrowband response, they're somewhat separated. Another way to adjust them, and it's kind of shown here, I don't know if you can see, there's little screws or rods in between the resonators coming down from the top of the housing, and they can serve to adjust the amount of energy from rod to rod and allow you to tune the coupling energy from rod to rod to improve the filter performance. Now, one thing you have to watch with these, as I'm kind of showing down here in the green area, is voltage multiplication. Anybody who's ever designed an LC parallel resonant circuit knows that the voltage at the top of the resonator can be higher than the input voltage by several times. And in this particular case, if this was a 100-watt filter, 100 watts, you would expect to see 100 volts at 50 ohms. But the voltage can get much, much higher than that inside these filters because of the resonant structures that are in play. In this particular filter, one of the rods is actually 5 times the voltage that you would have expected. And you have to make sure that the top of the rod has enough of an air gap or a gap to the metal wall of the housing so that you don't have arcing. Because if you have arcing, that would be a very, very bad thing to have happen. It could destroy the filter. If that would happen inside, you get that welding effect, and that's no good.
Okay. And what could you tell us about filter element properties?
So, as I said, these are inductors in parallel with capacitors, and a lot of times, and there is definitely resistance associated with the circuit, depending on the conductivity of the rods. Generally, the resistance is very, very low, and that provides you with a really high Q, high quality factor resonator, especially if you silver plate the housing and the rods. You can get very, very low loss. Q could be in the thousands, hundreds to thousands, definitely thousands range if you do it correctly. They're much better than an LC style filter. You know, in inductors, it's a lot of times difficult to get a quality factor of an inductor higher than 1 or 200. With these resonator structures, it's easy to get Q factors into the thousands, and the performance of the filter improves quite a bit. The losses are much decreased. The heat generated is much decreased, and as a result, they can handle higher power levels than your typical average LC filter.
I see. Well, can you give us an example?
Yeah, so this is actually not a diplexer, it's a triplexer, but you kind of get the idea. There are rods that are very specific distances apart, and you can't see it here, but when the lid is attached, there are coupling screws in between all of those rods that help to adjust the exact amount of energy that gets from rod to rod to improve the performance of the filter. Now, just to kind of look at this and analyze it, if you see the set of rods in the center would be the high band response because they have the least amount of capacitance to the housing. The ones at the top, you can see they're a little bit thicker, and when they get to the top of the lid of the housing, they're going to have a little more of a capacitive effect there. And so they're going to be the mid band. And then, of course, the lower row of resonators is going to be the low band response, and they're fairly far apart. Even though they're big and beefy, their distances are far apart. So you would expect the low band to be a fairly narrow band relative to the middle row of resonators, which is maybe a little bit more broadband because they're closer together. And I'll show you the frequency response on the next slide.
Okay, let's go there.
So there you have it. On the top left is the low band response. You can see it's very, very narrow bandpass structure. The bottom left is the mid band response. It's a little bit wider. And on the right is the high band response, and that's the widest yet. Now, the extra noise or response that you see on the right side of each graph, that's from something called re-entry. These resonators will pass. One of the negative downsides of this resonator technology is they'll not just resonate at a quarter wavelength, they'll resonate at 3/4 of a wavelength, and et cetera, et cetera. So when you get to higher frequencies, say about 3x your original frequency, you can get uh, another bandpass response out of them. And if you want to get rid of that, you'll need to put another filter on here, a low pass filter, to get rid of that. So that is one downside of these resonator structures, is that they do repeat in frequency at higher frequency levels. Now you can adjust that somewhat by shortening the rods. If the rods are shortened, you'll need more capacitance at the top of the rod, because shortening the rod makes it a lower value inductor. And a lower value inductor, if it's in parallel with a capacitor to resonate at the same frequency, needs a larger value capacitor. So you can shorten the rods to get them to repeat 5x, 7x, many times out from your primary fundamental frequency. But that comes at a cost of needing extra capacitance at the top of the rods. And a lot of times, to get that extra capacitance, you need to bring metal close to the top of the rod, and that lowers the power handling capability of the filter, because you can get arcing there if you're not careful.
Okay, and maybe could you give us a high power example?
Yeah, so here's kind of an example of that. This in the kind of the center picture, you're looking at a diplexer. You can see there are 2 rows of rods in it. They're separated by a wall. The upper left picture shows the wall and one set of the rods. Now, this is a 5,000 watt diplexer, and it can get that high in power level, because the tops of the rods are extremely far away from the top of the housing, or even from the walls or the sides of the housing. And the way that was accomplished was these rods are threaded in from the bottom, and they're as long as they need to be resonant at the frequency we need, just from the straight capacitance inside the housing. We don't have to bring a capacitor down from the top of the housing close to the top of the rod. These rods could be much shorter if it was a lower power application, but because this has to handle 5,000 watts, these rods need to be that far away from the top of the housing, so that they don't arc.
Well, excellent information as usual, Jim. How does Quantic Corry stand out in this area or similar areas?
Well, we're a custom design house. We have a lot of experience designing these kinds of filters and diplexers and any kind of multiplexer for that matter. But we'll work with customers to help them with their requirements, to make sure that we can handle the power and the size that they require. And we use lots of different filter technologies, not just these resonator style technologies. We use LC filters, coaxial resonator filters, microstrip and strip line filters technology. There's all kinds of ways to make filters, all kinds of different technologies, and I'm just going through one of them here. And we're fully equipped to use the best type of technology for our customers' applications.
Well, terrific. And I think we have time for at least one question. And the one that I got here says, would you ever want to use an LC type filter for these types of applications?
Yeah, that's a good question. Definitely. LC filters have the advantage that they tend not to repeat at higher frequencies like these resonant structures do. So if you have a particularly broadband application, LC filters are a good choice. The downside with the LC filters is their quality factor is not as good. Their losses are generally higher than these resonant structure filters. So you do get higher insertion loss, and you have to worry a little bit more about heat generation with the LC filters, but they're definitely great for broadband applications.
Well, very good. Thank you so much. And I think in conclusion, the bullets on your screen really sum it up nicely. If you are a customer and you have more questions, we'd love to hear from you. And you can call our engineering hotline. The number's on your screen, 724-940-7556, extension 276. And of course, there's no cost associated with these calls. Going forward, our next Tech Talk will be on Tuesday, July 9th at 1 p.m. Eastern, and the topic will be ceramic filter products. Thanks again to everybody, and thank you, Jim.
All right. Thank you for your time, everyone. Bye.